Okay, so let's take a look at how long it would take water to travel through this fracture for 300 meters. These are the characteristics. The hydraulic conductivity, 10 to the minus 6 meters per second. That's fairly typical conductivity for rocks at shallow depths anyway, in the Piedmont. The fracture aperture here, 10 to the minus 4 meters, that's 100 microns. A sheet of paper is about 75 microns, so this is a little bit bigger than a sheet of paper, but it's actually a fairly typical hydraulic aperture for a fracture. The fracture density, this is one fracture per meter, and the hydraulic head gradient 0.01, 1%. This is a reasonable value for a horizontal hydraulic head gradient. So all of these values I think are reasonable, and let's see what kind of time it takes to travel 300 meters. So we said that the velocity is equal to the flux divided by the porosity. That'll be true for any kind of porous media. And so in this case, for the fractures, the flux is the hydraulic conductivity, an effective hydraulic conductivity, times the head gradient, and the porosity we take as the aperture times the fracture density. So that will be 10 to the minus 6 meters per second for the conductivity. The aperture is 10 to the minus 4 meters. The fracture density is 1 per meter, and the hydraulic head gradient is 0.1. So let's take a look at the units here. There, those cancel, and we end up with meters per second, which is units of velocity, so that looks good. And let's go and do this calculation. If we go and write this like this, as 10 to the minus 2, then we multiply these two, we get 10 to the minus 6 times 10 to the minus 2 is 10 to the minus 8, and we divide it by 10 to the minus 4. It looks like the velocity is equal to 10 to the minus 4 meters per second. We could put it into our calculator, but we don't really need to do that. We can just work it out by hand. Okay, so 10 to the minus 4 meters per second, let's see, that's 10 to the minus 4, we said that was 100 microns, or a tenth of a millimeter. So that's, I don't know, that seems pretty slow, but if we take this out over a day, one day is approximately 10 to the 5th seconds. It actually is 806,400 seconds, but we just round that to 10 to the 5th seconds. And so if we think about this velocity over one day, we see that there's about 10 meters of movement over one day. So that's actually quite a lot. We can go ahead and complete the calculation by saying that the travel time is equal to the distance traveled divided by the average velocity. So that's 300 meters divided by 10 to the minus 4 meters per second. The meters cancel, and that's going to give us 3 times 10 to the 6th seconds, and that's just about 1 month. So that's the time that it takes for water to travel 300 meters in this fractured rock.